And good morning, everyone. It's interesting to do this guest lecture in Corona time online. Everybody's now online connected. In an old world, we would all sit together in a classroom or in an amphitheater and talk. But hey, we just got to do what we got to do. So let me introduce myself. My name is Simona Mihaitsa. I'm a senior lecturer in the University of Technology, Sydney. And today I'm going to talk to you about how we're using data analytics and all sorts of machine learning for doing the transport modeling, because this is the class that you've had, Introduction to Data Analytics, and I thought that it would be very appropriate. So I'm going to tell you a bit about who we are, in case you haven't heard about us, what impact we had, and what we are passionate about in the Future Mobility Lab at UTS, what challenges we're facing. Also, one of the case studies that I have chosen to talk about today is mostly around incident duration prediction using all sorts of machine learning algorithms, because this is something that you have just recently learned about, and I thought that it will appeal to you. So I'm going to talk why it's hard to solve this problem, the data that we have used, what methods, algorithms we have used, and of course, what results we have had. So without further delaying, we are part of the Data Science Institute. 2 years ago, UTS put this Data Science Institute together, and there are almost 35 full staff academics in there with different domain of expertise. The core expertise of the Data Science Institute is mostly around data science. So there are people who investigate and do a lot of research on how to invent the best machine learning algorithms, deep learning, how to apply all sorts of anomaly detection methods, right? And mostly all the hardcore data science part. Also, then there are people who are using the data science applications and analytics in order to solve real world problems. The first application domain is transportation, and this is the one that I represent and the one that I'm going to talk about today. Mostly we are interested in solving problems which relate to how can we simulate transportation around the city, how can we optimize it, how can we control it. We are using a lot of genetic evolutionary algorithms and do a lot of work around public transport as well. But there are also other people who apply data analytics, for example, for solving energy problem. Whenever you think about, for example, short-term energy demand forecasting or fall detection, this can be easily applied to energy. There is a large group working in water, water research, anything related to water pipe failure prediction, and predictive analytics for sewer corrosion, all that kind of stuff. There is also a very interesting domain that the group has started to recently study, which is human in the loop. It's basically how can we embed the human social behavior into machine learning? How can we keep this into account? So as you can see, data science can be applied to a lot of domains, not just one. So it's fantastic because you can have a lot of different expertise, different background, but still get some interesting results. There are some awards that we have gathered because previously we were part of CSIRO. So for many years we have been working together, and we continue even in UTS. We have just recently won the 2020 Victoria Eye Awards for doing an NBN broadband service demand forecast using, again, AI algorithms. And we have just been listed in 2020 as finalists in ITS Australia Awards for improving train network performance using all sorts of machine learning techniques. So there is recognition to what we do. Inside the Data Science Institute, this is the Future Mobility Lab, and I am representing and I'm leading this. If you're going to go to fmlab.org, you're going to see in there all the domains and all the topics that we're passionate about, and starting with how to simulate different modes of transportation, how to do data analytics for public transport around Australia, and applying all sorts of deep learning algorithms and for even lane-based flow prediction, for example. But the problems that we want to solve in general in the Future Mobility Lab are basically residing in a few questions. We want to understand, for example, why traffic congestion appears in the city and where. Also, why, if you, I mean, all of you have probably traveled by transport in Sydney, taking a train, taking the buses, there's always delay that is being accumulated. And it's very hard and challenging to understand where delay accumulates, but most importantly, why delay accumulates. So is there a way that we can use data science to be able to investigate that? And also what we want to be able to use these algorithms into is to understand if we can make the difference between regular traffic congestion versus abnormal traffic congestions, like disruptions, right? The way people move is also very important, how people make choices. Why do people prefer specific modes of transportation over the other? And what influences our choices? So this is also one of the areas that we are passionate about. Anyway, feel free to have a look and score through. In Australia, as you know, Sydney is the largest but the most congested city. So it's interesting because the cost that comes with congestion are usually very high. And if you have time and you're passionate about, you can search on the Tomtom Live Congestion Index. This is a site that I like to use a lot because it tells you for many cities around the world how the congestion level is fluctuating from one day to another, 1 year to another. Interestingly, in the same period on 22nd of October last year, congestion around Sydney was around 73%, and it was really going up from 2018 even. This year is a total special situation because we have the COVID. A lot of people are working from home, and people we are not traveling as we used to do. So congestion is up, is going down actually to 56, which is fantastic for the city, but still very high. So also the site tells you as well how many days you can save by not being stuck in congestion, and you can spend using your favorite TV serial or something. Anyway, have a look. So in the approach that we are taking when we're doing transportation modeling, there are majorly two streams that we are taking. And it's all depending on the data sets that we have available. So I have listed here a few. We normally deal in transportation with historical traffic data sets, and these are many times stored in some databases, some repositories, and traffic agencies do not use it, don't know what to do with it. We have, for example, timetable data of trains, ferries, light rail, you name it, anything that is public transport. One of the data as well that is extremely valuable is passenger data, and this is your Opal card data. So whatever you do with your Opal card, it's being stored, and basically your activity together with all the people in the city activity reflects specific behavior. So that is very valuable to us. We also use, for example, data that comes from the traffic intersections. It's called signal control data, networking data, and sometimes we also have access to real-time streams of data sets. So for example, the traffic around the city is monitored using embedded loop counters, and this gives you, with a high frequency of every 3 minutes, traffic flow, speed, occupancy, for example, and you can use that for doing the modeling. All of these data sets that I have just presented, they have something in common, and that is the fact that they are repetitive. They are coming in streams and time series, and they present patterns. So this is very important because whenever you have data sets which have patterns in them, it's very easy to apply a data-driven modeling. So you can do data analytics, you can do predictions, and so on. And you can detect these patterns from the data sets. What can we get out of? I have just listed here, for example, we can do some analytics investigation of how people choose their modes of transportation. We can predict, for example, the traffic congestion. When I say this, I mostly refer to prediction of flow or prediction of speed. We can also do analysis of delays, dwell times, and so on, all sorts of correlations. So this is something that you can do as long as you have a reliable and complete data set which presents patterns. However, traffic is extremely unpredictable. And as you know, a lot of times there are incidents that can happen anywhere into the city, and mostly they have a large diversity. We call this incident data sets. And even some external events that can happen into the city which have not been predicted. For example, if the traffic management center, they need to close down a road section and deviate the transport to some other road sections. If you name it, if there is some protest, just like we recently had, all sorts of events that these are not planned, and this can happen anywhere at any time. So these don't really have patterns, because every time they happen, these are new. These have never happened before. They can have different impact. So basically for us, this is a different type of data set that requires a different type of thinking. We call this non-recurrent traffic modeling. And for this one, we're using traffic simulation. So to simulate what would be the impact of a specific disruption, how can we respond, how can we optimize some sort of timetables, and so on. I'm going to give you at the end of my presentation a snapshot of what exactly it is simulation modeling that we're using, but mostly I'm gonna focus on this one. So the application that I chose today to show you how we have been using machine learning algorithms is around the arterial incident duration prediction. And let me go through this with you. There is a cost associated with every accident that happens in the road. You need to know that. And the problem is very hard simply because there are many factors that can influence how long traffic are going to last and how long it will take for traffic agencies to clear them off. If, for example, the incidents happen in a very congested part of the network, with a very high intersection, let's say like a very complicated intersection, if it's during AM peak or PM peak, it is extremely important. So also if there are fatalities, unfortunately, this will impact the time that it takes to clear off the scene and get back to normal. So there are some traditional methods that have been used previous to our studies, some Bayesian classifiers, some discrete choice modeling. These are all, how should I say, presented in the literature. However, majority of the work has been done for motorways. So motorways are much simpler to analyze, simply because you mostly have one way, and in general, you either block one lane, two lane, or very rarely you block all the lanes on a motorway, even if you have an accident. However, when we're talking about incident along arterial roads, like regular roads into the city, especially if they happen in a major intersection, you tend to block all lanes in all direction, and this is quite hard for traffic operators to handle. So in terms of the data sources that we have used, we have received from the Traffic Management Center in Sydney. In 2017, we had around 5,000 records of all sorts of incidents. You can see here the layout of the area that we have been looking at. So this is Piermont in Sydney. This is Rozelle, and this is Ryde. So these accidents were, they were spread across the entire network, and they came with all sorts of, how should I say, severity levels and so on. For our study, we mainly focused on accidents because accidents are the ones that take the most to clear off, and they are priority for traffic centers. The rest, if it is a hazard or road closure, it's much more easier to handle, but still accidents are hard to handle. So in total, we had around almost 600 accidents. There was with a mean duration of 45 minutes, and some of them even went up to 719 minutes. So all this for us, it's information. So how do we translate that into our algorithms? So for us, all this information, they are features. So we separate them into different categories. So for example, this is the category which looked at accident characteristics. So we had the location, we had the date, which we split in hour of day, whether it was a peak hour or not, day of the week, and so on, time of the day. And then we also had information about severity, direction, affected lanes. We added on top the weather. So we collected weather information into the entire network, and we added as features, to our data set. We added information about the public holidays, whether it was not or public holidays, this can influence as well. And also we added features and information around the area where it happened. So basically, for example, what was the speed of the section which was affected, how many lanes, what street ID, what intersection ID, and so on. So all this information was part of our data set. When we did the data profiling, the next step, we realized by plotting, as you can see here, the histogram of the incident duration, that the majority of incidents, they were being cleared off in less than half an hour, which was great. But however, this is a long tail distribution. So what does that mean is that you have at least 10% of the accidents that fall into this range. And this means you don't have enough information, previous historical information, and they are very, very hard to predict. So when you're doing your tailoring models, you need to be very aware of how your data set looks like, what you want to predict, how it's distributed. Also, when we plot the empirical cumulative distributed function, we realize there are almost 2 regimes, and these were split around 45 minutes into our data set. Like incidents with less than 45 minutes were clearing off differently than incidents longer than 45 minutes. So basically, after that, we wanted to see, okay, that is great. We have all this information, but we are traffic modelers. So we want to understand as well how traffic information can help us to better predict the incident duration. And we wanted, on top of the features that you have seen earlier, we wanted to add traffic flow features. So around Sydney, traffic flow is being counted by what is called SCATs, traffic counts. And here, this is a mapping of this count loop detectors along the city. As you can see, there are major roads that are being monitored, but unfortunately, there are sections like this area over here, for example, which have no traffic flow information. So this means that if you have accidents that happen here, we don't have information with regards to the traffic flow at that moment in time, at least not from TMC. And they don't monitor every road into the city. So this was quite a limitation, but at least we had, in total, I think we had 85 intersections, and we had, I think, around 4,000 something SCATs detectors that were giving us data. So it was still good. So when we had to add that in, what you need to know, you need to do a mapping. So for example, this is the location of the SCATs count detectors, and we had to map each of these detectors counting vehicles to each of the lanes of the network, because you need to know exactly for each lane, for each road direction, how many cars were being reported or not. Otherwise, your models will be messy. So we did this mapping, and then we had to think of a strategy to embed the traffic flow feature. So for us, the traffic congestion can be represented in 3 ways. So we took the traffic flow in the 15-minute time interval when the incident was reported. I forgot to say that the traffic flow information is being recorded every 3 minutes, and we aggregate it in every 15 minutes. So we looked at the 15 minutes time interval where the accident happened. We took the reported real-time flow, we stored it, and we also looked 1 hour prior to the accident. And not only that, we did the ratio between what is happening now versus what has happened 1 hour ago. Because basically, if this ratio is going down, then you need to, it shows that there is a problem and that congestion accumulated and so on. So we had 3 different measures of the traffic flow, and this allowed us to build several scenarios of how we construct the features. So the first scenario was just take the features that we have, the one that you have seen in the previous table, and we built what is called a baseline features dataset. and perfect. We use that one for training our models. But then when we embedded the traffic flow, we build other scenarios. I just named them FSA, B, C, D, in which we played with the way that we embed the traffic flow features into the model training. So for example, this feature dataset A, we would take all the traffic flow counts from these three measures on all the road sections into the network, right? It was a lot because we had almost 700 extra features that were adding to the model training. So this makes things very, very hard to handle, but we wanted to see whether it's working or not. But then we also did some tests. Hey, how about if we aggregate this traffic flow features? So for example, in FSB, we just chose the top 5 closest road sections to the incident location. Then we aggregated as well the traffic flow for this 5 section. And lastly, we did also a radius. Basically, we started from the location of the incident and we started looking at traffic flow at 100 meters, 200 meters, up to 600 meters away from the traffic incident duration, traffic incident location, so that we will see how far away the congestion will spread. And it was, I mean, we wanted to know, right? You never know when you're doing this type of analysis, what's working, what is not working. And the method we have basically applied, so it goes like this. So we took the baseline feature dataset, the one that you have seen, and firstly, we did the classification prediction. What does that mean? We wanted to see firstly, whether the incident will be less than 45 minutes or not, because this is an easier problem to solve. If indeed we have short-term accidents, that's fine. We apply a regression and we put the traffic flow features on top and we apply regression directly to predict more precisely how many minutes the accident would last. However, if there are longer incidents, more than 45 minutes, this is a very complicated problem, as you have seen earlier. We're facing with long-term incident duration prediction, and this requires not only the traffic flow data set, but you need historical traffic flow in that area to build the patterns. We need to build graph congestion propagation, NLP, and so on. So this is much complicated. So let's focus here. So for the incident duration classification part first, so all the features that you have seen, basically we put them into a matrix, right? And we build this X matrix. And then all the durations, we put them into this vector, Y, which is the duration of incidents. And basically, what is the classification problem? We just want to predict this vector of incident duration using this matrix of features, right? And it will take a value of 1 if indeed our incidence is less than 45 minutes and 0 if it's more than 45 minutes. We tested various methods. We tested the KNN, we tested the localization regression, random forest, gradient boosted decision tree, and also another type of decision tree, which is the XGBoost, which is an extreme boosted decision tree. It's a bit special. You might have studied some of these models so far. They all behave differently. For example, the GBDT builds trees and the leaves, the final leaves of the trees, these are the ones which give you the final predicted class and so on. Without getting into details, what we did, we basically did a 5-fold cross-validation for the classification part. We divided the data set in 5 subsets, and basically we just, we used each fold as a test set, and the remaining 4, we use it as a training set, right? And what we did, we fitted the parameters of the models on the training set, and then the prediction we have done on the test set. For evaluating, we have used the accuracy prediction recall and F1. These are based on the true positive and true negatives values. The most important, I would say, is the F1 score, this one, which gets this format here, simply because it's a combination of precision and recall and shows best how your model is performing. In terms of the XGBoost, why did I say it's a bit special? It's an enhancement of GBDT, simply because it has a regularization parameter in the learning objective function, right? And this is mostly to control overfitting. It's very good for a parallel tree learning, right? If you have multi-core processing. So basically, if you have a data set, the interesting part is that this model uses a sum of additive function. So as you can see here, F, right? And based on one function for each number of generated tree that you have. And these functions are expressed like this. It's basically expressed based on the weights of each leaf that you have into the model. Finally, the objective function of XGBoost is written like this, and this is mainly the MAPI. So we used initially, we use various of them, you'll see later. This, let's say it's a MAPI function, and then this is the regularization parameter, right? Which gives you the complexity of the model. Anyway, we use different performance metrics evaluation for the regression. We don't use the same as for classification. So to evaluate the models, we have used the MAPI. This is the mean absolute percentage error, and we have used R square. When we did the hyperparameter tuning, we use randomized search. What does that mean? We basically just select a small number of hyperparameter configuration to basically use them for the validation. And we had, I think, around somewhere between 100, 200 random samples. So in our case, the random search, for example, was better than research. So this is the 10 cross-validation setup. We train each learner for 10 times, multiply by the number of hyperparameter tuning fold, which was 5, and also we chose 500 number of hyperparameter combinations at the end because we thought it's better. So in total, 25,000 times, right? It took about 10 minutes if you have a good machine. We also selected the most important feature, and basically we wanted to see a ranking of all these features, how they are, the importance that they have into the model. And for this, we use shapely value. Shapely value comes from game theory. So you have n players and you have a coalition of these players. And the way shapely value is calculated is basically is trying to see the weight of each player in order to distribute the whole gain that the coalition has. So this is just a mathematical expression, but basically what it does, it just takes out each of the player and reevaluates the gain so that basically it's a fair distribution among players. So some results, these are the results for the incident classification. So these are the plotting of accuracy F1, precision and recall for all the machine learning models that you see here. And I mean, if you have to look individually at them, for example, let's have a look at accuracy. You realize that Canon is the worst performance, right? And then you have random forest, right, for this case, which gives you the higher score. However, have a look, random forest here is basically a bit overfitting. But F1, let's have a look at F1. I think this is the most important, right, from what we need. And if we look at F1, GBDT was the one that gives us the highest F1 score for best training and testing, right? And it was very close to XGBoost. Again, a random forest is overfitting. So this gives us some indication about what model works best. When we looked at the incident regression, we also did some, this time, some outlier removal. So we wanted to see how the models are performing. For example, if we remove accidents less than 1 minute, 2 minutes, up to 5 minutes, why? A lot of accidents also, for example, they had 0 minutes records. This is not, it's a data that is not bringing you any useful information. You can't really have incidents with 0 minute or 1 minute. That's not really an accident. Something must have happened in there. Either it's an error in the data sets and so on. So we looked at the performance of GBDT and XGBoost when we remove gradually the small incident duration. And indeed, it's a huge performance improvement. So for example, GBDT went from 2 to 1 up to 120. We also did in the log space and it went out to 83.26. So it's really good. XGBoost performed even better. So when we compared all the models, so we had 4 regressors mainly that we chose. We had 3 training measures. So we trained with MAPI, each model, and then we trained with MSE, and then we trained with R2 just to see which one would be the best fit. And we evaluated using MAPI, and then we evaluated using R2. So this is a plot of the MAPI results with 2 different performance metrics. Have a look. So XGBoost is the one which really is the best performing, but only when we train it with MAPI. And same here, if you look at R square, you want your R square to be as high as possible. Well, actually, yeah, so in our case, the XGBoost was around 0.78. An ideal R2 would be around 1. So it's not ideal, but still, these 2 performance metrics tells you the same story. The fact that you basically have XGBoost, which is your best performer when it's trained like this, when it's evaluated like this. So that was interesting. And when we lastly do, this is the last thing that I want to mention, when we did the feature importance, have a look here with using the Shapley value. The blue means lowering the incident duration and the red means increasing the incident duration. Have a look here. Location is very important, of course, but hour of the day. So what this tells you, for example, have a look. The more the hour of the day increases, this means the less your incident will be in times of duration. Why is that? For example, when you have an incident happening at 11 p.m. in the night, it will be much easier to repair and readdress everything than if you have an incident at 8 a.m. So at 11 p.m. you have less congestion. The affected number of lanes, of course, have a look here. The bigger the affected number of lanes it is, then your incident duration will increase. So this tells you that different features have different weights, different impact on the results that you have. And lastly, basically, when we compared all the scenarios, the FSA was the best one performing in terms of MAPI evaluation, going up to 55.28. So what this tells us is better just throw everything you have into the model. Apparently, it's not such a big difference between them. However, when you use all the information you have, your models are performing better. And this is the last video I think I want to say. So I talked so far about data modeling, and this is just a snapshot to give you when we don't know how to predict, right? We are basically just simulating the accidents. So this is the same area that I have been working on previously, and we built the traffic simulation model for this area. The same idea we had to model the impact of incidents. So this is Piermont, Roselle, and Ryde with all the traffic intersections that are signalized. And it was interesting enough that this was I mean, all the mornings are special, but at 6:45 in the morning, you have regular traffic. And this is quite a busy area because you have all the traffic going from Ultimo to Anzac Bridge to the west. So everything is running fine. The traffic signal controls are running fine, not a problem. However, accident starts to come. 7:34, you have already a reported accident which blocked both directions. So congestion starts to accumulate. This was a lucky case because it only lasted, I think, for 4 or 5 minutes. So not such a big impact. You do have cars accumulated, but once it stops, traffic, it's easy to get back. So you can see it stopped, traffic goes back to normal. So the traffic management center does not have to do a lot of interventions here. However, when you have, for example, at 8:06, there was an accident which was reported here, the exit towards the Anzac Bridge. So all the exit was blocked. And this one, unfortunately, lasted for almost half an hour. So when you have accidents going for half an hour, then you start congestion accumulating and building up into the network and spilling back. So it starts spilling back into the network, and you need to know what other intersections are being interconnected so that you make the proper actions, right? And I think there was another one. Yeah, this one didn't even clear off. So there was another one here on the Anzac Bridge again. So you have, this is what traffic management centers are dealing with. Multitude incidents happening in the same time. They have different weights. They have different impacts. So the traffic simulation model, it's best to give you this impact. Anyway, so at the end, you can extract all the performance metrics. You can build scenarios. What if I would change, for example, green time, red time here? What if I give more priority to this guys, and so on. If you want to know more, feel free. I think I consume my time. There is more information online. This is a presentation that I recently did. It's recorded as well for, it was the graph modeling approach for motorway traffic flow prediction is online. Go ahead, have a look. And also, we also worked on a problem for dynamic trend demand estimation for all the entire Sydney train network. It's quite huge, 506 platforms. We had to estimate and recalibrate almost 3 million time-dependent OD matrices. So if you are interested in that, have a look on our FM Lab website, or have a look in these links. And yeah, I mean, if you have any questions, let me know. I can take some of them now before the next speaker. And also get in touch if you have questions, if you want to do a PhD in transport, if you want to study any problems of transport modeling, yeah, just let me know.
Yeah, thanks, Simona, for your great presentation, and you have a very interesting problem to solve using the data analytics techniques.